My name is Jay Sandayan. I'm the director for Center for Sustainable Infrastructure and Digital Construction at Swinburne University of Technology. So I will talk mainly about the work we are doing at Swinburne and also the major issues and confronting the construction industry at the moment. So mainly the issues are sustainable construction, and we are trying to solve this by digital and automation technologies. So what are the main issues in sustainability in construction and how automation can improve the sustainability? So number one issue in construction at the moment is waste generation. The construction industry, construction and demolition industry, they are the largest waste generator. About 36% of the total waste generated by human beings are coming from construction and demolition. And the waste generated by construction sector just in Australia is about 2.4 tons per person. 44% of that is from construction demolition. The previous 36% mentioned was about world global average, but in Australia that's 44%. And the issue with this kind of waste is they are difficult to dispose, and they cost, they're heavy. And in Australia, we spent about $2 billion in disposing these waste, compared to manufacturing that's about 1.2 million, and household spends only 0.6 million. We spent a lot of focus on household waste, but very little is on construction waste. So that's what we are focusing on. And let's look at this graph where you can see the waste trend per capita in Australia. The municipal and household waste, they are on a decreasing trend, as most of us know that we spend a lot of time putting different waste in different bins and recycling a lot of our waste. Manufacturing and commercial industries, they're more or less maintaining their waste despite increasing production. But construction and demolition, they are on an upward trend. So that is a major issue compared to in 2014. That's about 0.75 tons per person in Australia. That's gone up to 1.06 in 2019. That's the data we have up to then, but it's going up more. So why construction is generating so much waste is because processes are very inefficient. If you look at most of the construction site, you see a whole lot of rubbish sitting everywhere. And in fact, 30% of the new materials they order are returned as waste. That means they order too much. In addition, temporary works, form works, and timber. So we actually build a structure with timber first, and then we pour the concrete, and we take the timber and throw it away. So that is a huge amount of waste. And also damaged items and excessive items and so on. So if you look at a construction site, it looks heaps of mess, lots of timber. All of those timbers are just gone to waste. The other important issue is the cost, because the cost and affordability, the waste contribute to the cost, but in general, the productivity is not going well. That's because we, in construction, mostly we are still relying on manual and heavy labor-intensive work. So this is a very famous graph put out by McKinsey's. You can see the manufacturing sector's productivity is going up, and you know that things are getting cheaper and cheaper, most of the manufactured good. The total economy is also generally going up, but construction sector more or less remains the same in the last 30, 40 years. Nothing much changed. Why is that the case? Is because if you look at automotive, aerospace, and manufacturing industries, they use CAD modeling, computers, additive manufacturing technologies, automatic assembly methods. You look at a car factory in 50 years ago and you look at the car factory now, most of it's automated. That's why most people can afford a car now than maybe 50 years ago. Whereas if you look at a construction site, they're very low labor efficiency. You see a lot of people doing manual works, and the accident rates is the highest in construction industry. And quality control. How many of us having to deal with builders, things are not done well, and it's a constant issue. Whereas you buy a car, they guarantee for 7 years. Normally, we don't have an issue. The productivity is also reflected in the prices. So I just plotted a price of an average car since 1960s. It's actually gone slightly down compared to the wages, whereas the construction of a house has gone up significantly. So that's one of the factors that is contributing to the homelessness problem in the worldwide. If you look at it, 1.6 billion people live without proper housing. 1 in 7 people on the planet currently live in slum, and that will change to 1 in 4 in the next 5 to 10 years. So these are the issues facing us. The other is the carbon emissions. Concrete is responsible for about 11% of the carbon emissions. Steel is about 10%, and so on. But the concrete is a major issue because it is the largest man-made material we consume worldwide. It's around 23 to 25 billion tons worldwide. The next item we consume is coal, oil, and steel, plastic. They're all smaller. So if you want to focus on sustainability, we should focus on the largest material we consume, that is concrete. Only other material that's consumed above that is water, which doesn't produce any carbon emissions. So sustainability is the issue. And let's look at manufacture of Portland cement. It's based on, we take the limestone from the ground and we mix a bit of clay and shale, and then we the raw materials are mixed, and then they are burned at very high temperature in a kiln that between 900 and on the other end it'll go up to 1450 degrees, and that produces the clinker. And then the clinker is ground with gypsum, a little bit of 2% gypsum, and that produces Portland cement, which is the cement that we use. But the main issue is not the energy, because the energy, when we go to renewable energies and other less carbon intensive energies, we can solve the energy heating issue. But the limestone, the production issues, production of Portland cement involve decarbonizing the limestone, calcium carbonate. We need calcium oxide. So we have to release the carbon dioxide into the atmosphere. There's no way out, even if you 100% renewable energy, this process is going to continue emitting carbon emissions. In fact, after fossil fuel, cement production is the next item that produces global carbon emissions. So the cement production worldwide is on the rise, mainly from the developing countries, because they are still developing and catching up with infrastructure. Whereas if you look at Australia, we are on the downside curve, because most of our infrastructure is completed, but we are still consuming about 12 million tons of cement a year, but that's kind of stable. But whereas if you look at developing countries, they are still on the way up, because they are still catching up on infrastructure development. So the cement production and the carbon emissions due to cement production is significantly on the way up. So this is the major problem. So you can see the total cement production is going up, mainly because of other developing countries and India. But China, for example, they are just peaked because they have done most of their infrastructure, and the other OECD countries, they are more or less on the stable path. So we have to find alternative to cement, because this is not sustainable. So there are alternatives available. This is geopolymer concrete is one alternative.
So geopolymer concrete is it's an alternative material. If I explain it in simple terms, so geopolymer has two types of, like geopolymer, we need two materials. One is the aluminosilicate precursors, and the other one is the alkaline activators. So aluminosilicate is the material rich in alumina and silica, and the alkali activators is alkaline solutions. They can be in liquid form, they can be in solid form. Like examples are like sodium hydroxide, sodium silicate. Those are the activators. So the precursors, the common example, fly ash slag. So simply when you combine these precursors with the activators, they form a reaction product. So that is the geopolymer. So in concrete, instead of the normal cement, we call the ordinary Portland cement or OPC, you can replace that cement with the geopolymer. So when you replace that, you get in concrete, instead of cement, you can replace the geopolymer, you get geopolymer concrete.
Slag sounds like a waste for some people. In a way, it is. So it is a byproduct from industrial waste called blast furnaces, specifically massive furnaces where iron ore is smelted to create molten iron. So within iron ore, oxides like silica, alumina, magnesia, they are combined with flux, normally limestone, and produce glassy substance. So this glassy substance is lighter than molten iron, therefore they are floated on top of heavy iron. We can carefully skim off. So it is not waste anymore. It is a resource for concrete industry. However, we have to go through two-step transformation before we use this material into concrete. So firstly, we have to rapidly water quench this molten slag. Molten slag is around 1100 degrees Celsius. We have to rapidly cool down to avoid crystal from forming. So after water quench, this material has glassy non-crystal phases. It can be reactive within concrete. So we call this granulated blast furnace slag or GBFS. This large pile behind me, it's called granulated slag. You can see this has a sand-like particle size distribution. So we have to go through another transformation in order to get its finer particle size distribution. We call this a milling. So second transformation step for granular slag is we have to grind it. So without grinding, we don't have a proper reactivity in concrete. So in Yaraville, we have a vertical roll mill or VRM to grind the slag. This granular sitting here is ready to feed into a VRM. So after grinding, we get the fine particle size similar to cement and ready to use for concrete. After grinding process completed, we can get very fine slag powder. We call this ground granulated blast furnace slag or GGBS. So now this material is ready to use for concrete as a partial replacement of cement. So in Victoria, we can use 30 to 50% slag as a replacement for cement. So slag has incredible latent stage hydraulic properties. It improves the longer term strength development and also advanced microstructure in concrete. So it is not just a filler material, it's actively participate for reaction mechanism. So during hydration of cement, it produces a product called calcium hydroxide. It can react with supplementary cementitious material like slag and produces additional compounds, which makes concrete more stronger and durable.
These are alternative materials that can replace the conventional Portland cement, and that can reduce carbon emissions. So these technologies are available, but it costs to adapt this education and other things that are needed. See, if you look at construction site, because of the heavy manual labor that is required, mostly people work there with strong physical abilities. However, if you go into automation, we can employ workers from a diverse range of abilities, and that open up the labor market to half the population, women, plus also men who are not that strong. So these are the advantages of digital and automation technologies. So the emerging technologies for building without formworks, there's two technologies that we're working on, but there's a number of different other technologies as well. So there's digitally adaptable formwork. So instead of making multiple formworks for each shape, so we use one formwork that's digitally adaptable, and the other one is 3D concrete printing. So let's look at a structure like this, where you see a shape which is not square and rectilinear. And to make multiple panels for this shape in the 1960s when they constructed, they made for each panel there was a separate mold that was made, and the concrete was cast, and then the molds were assembled. So there's a huge amount of molds that were made, and they were all waste. So what we have come up with is a digitally adaptable flexible formwork.
So you can see there's some actuators. We just automatically control the actuators to different shapes to make the different and the curve, and then we use our developed printers to print the panels.
So we divide the shape into multiple pieces, and then those pieces are numbered. So we have some 80 different pieces for this particular structure, and the computer can control when we put that number, that will go into that particular shape, and then we can adjust it, tweak it if you are not happy with it, and then cast the concrete on top of it, and then go into that shape. And then once the concrete's hardened, we take that piece of concrete and then we assemble them all, and that then can create that shape. The other technology that I mentioned is 3D concrete printing.
So concrete 3D printing is a concrete placement method. So we don't need formwork. what we have to do is we have to just make our concrete mix, and then we have to use a concrete printer and we can place it along the path that we need. So in concrete 3D printing, we place the concrete by layer, thin layers, you can see. So we have a layer by layer structure. This is how you see it from the side. But if you see it from the outside, you can see it's a one single material. So just because we are doing this layer by layer arrangement, we get this kind of texture, but it's not separated from the inside. And in 3D printing, the material is very important, because now the material, when we have our concrete mix design, it should be flowable or loose enough to come through the pipes and the nozzle. But soon after it exits the nozzle, it should be hard enough to keep its shape. And also when we are printing on layer by layer on top of that, the materials in the bottom layers should be strong enough to withstand the weight of the top layers. So it's not simple when we are doing 3D concrete printing. We have to put a lot of effort to develop a 3D printable mix. And here in Swinburne, we do a lot of research related to the material side, and we print with the conventional materials. For example, this one we have, this is a 3D printed truss with a normal concrete. So that means we have already Portland cement as the binder. And if we come to this one here, you can see there is a clear difference in the color. So this one does not have any cement. So what we have in this is, instead of already Portland cement, we have replaced it with the low carbon binders. And this one has the geopolymer binders, which are made with waste clay bricks. It is a source of calcined clay. And then we have fly ash, slag, and some additives. So this one is cement free. So this is, compared to this one, more sustainable. And so you can see there is another one here, and is the same shape, but again there is a difference. So in this one, what we have is the geopolymer binders with waste clay bricks plus natural sands. And this one, we have replaced the natural sand 75% with the recycled glass. So compared to this one, this is more sustainable, because we have incorporated more waste and more recycled sources to this one. So likewise, in Swinburne, we do a lot of research due to the material, in the binders aspects, in the aggregate aspects, how we can make 3D printing more sustainable in terms of the aspects of the material.
There are a number of issues that need to be sorted out before 3D printing can be a successful technology. And one of them is buildability, because when we print layer by layer, the concrete is still fresh concrete. It can just collapse like that. So the main issue is the yield stress. Yield stress of the fresh concrete is the key rheological parameter, and that need to be understood carefully. So we came up with a formula that complies with a Moore-Coulomb model. So we come up with a formula. Based on that formula, we can predict the height at which the 3D printing layers will collapse. So as I said, there are a number of issues that need to be sorted out. There's the buildability, as I mentioned, is based on yield stress. The concrete need to be extruded. So that again is another property of the concrete. And also the concrete need to be pumped. So for the concrete need to be pumped, it should be workable. That means it should be fluid enough. And it should have enough open time. Open time means the time between the concrete is mixed and the time it's go hard. It should be sufficiently long. So the concrete should be fluid enough for pumping, but when we're building, it should be stiff. So we are asking two different things from the same concrete, which is very difficult to achieve for concrete. So one of the technologies that we are exploring, and we have been successful to some extent, is vibration-induced active rheology control. So the rheology is controlled on demand. So when we vibrate the concrete flows. It increases the workability. So we take a very stiff concrete and we vibrate it during pumping, and that makes the concrete flowable. And then when we start printing, we stop the vibration and then it becomes stiff again. So that is one successful technology that we've been working on. And the other is a short duration near nozzle mixing. So we bring the concrete, we don't mix the concrete before we pump. We bring the dry materials to the nozzle and we mix it very quickly and then we print it. So the mixing time is only about 15 to 30 seconds. So it's very short time and then it's mixed. So that concrete, we have designed the concrete to set so quickly within a couple of minutes and then it's strong enough. So conventional concrete, we mix between 5 minutes to 10 minutes to achieve the uniformity. Can we achieve the same uniformity by mixing 15 to 30 seconds? Yes, we have come up with a technology that can do that. In addition, when we finish printing or when we have to stop for lunch break or coffee break, we only have to clean that part. So we don't have to clean the whole concrete pump and the mixers and everything. So that is a big advantage. Anyone tried to do 3D printing, washing is a big issue. So we did this mixing with 15 seconds, 30 seconds mixing, 90 seconds mixing. And as you can see, we can achieve a very good quality print using 30 seconds mixing. So as I said, this can save a formwork, but we also need to work on cement alternatives. So cement alternatives are geopolymer concrete, high supplementary cementitious replacement. So we replace part of the cement with slag or fly ash and calcined clay. Normally, we can do by 25% of the cement can be taken off and replaced by other non-emission materials. But geopolymer concrete is a concrete we just replace all of it. 100% replacement. There is no Portland cement at all. And this technology has been available for about 28 years now. And also we have a number of projects, especially Melbourne and Australia are the leading country in terms of building them in real life construction. There's about 18 projects, successful projects in Australia using geopolymer concrete, including an airport in Toowoomba was built using geopolymer concrete, and there was a building in Queensland and also a bridge structure in Melbourne. Yet we don't use geopolymer concrete widely, and it's actually we don't use it anymore. The companies that started with very high hopes, they are not they're not financially doing well because the construction industry are not happy with certain way the geopolymer concrete behaves. Maybe it's a little bit sticky. The concrete construction laborers don't like the way certain behavior because they are expecting exactly 100% like conventional concrete. It's because if it's a little bit changed, that requires for them to adapt and change, which they are not willing to do. However, when we introducing a totally new construction method like 3D concrete printing, there comes an opportunity where you are learning the entire system totally new, and we can introduce new materials which are sustainable, and there will not be any much resistance because we are learning everything new anyway. So we have printed with geopolymer concrete, which inherently sets quickly, which is seen as a negative in conventional concrete. But when we 3D printing, we bring the two components together and mix it and then print, and then it sets so quickly we can even print horizontally, and you can see there's only a small sag in the printer. This you cannot do it with conventional concrete. The other geopolymer concrete that we are developing is using powdered waste clay bricks. So there's a lot of waste coming from construction and demolition due to bricks, and we grind the brick to a powder, and then we use activator to make it into geopolymer concrete, and we can 3D print, and it's nice color as well, and it reduces carbon emissions by 80% compared to conventional concrete. And we can also use waste clay brick combined with waste glass to make geopolymer concrete, and as you can see, we can get very high strength, so there's no issues with strength, and these technologies are available. It's just a matter of willingness for the construction industry to adapt it. The other major issue everyone point out immediately when we get 3D printing is reinforcements. How do we put reinforcement, the steel reinforcement, inside? We got a solution for that one as well. So we developed an in-process mesh reinforcement technology. When we modified the nozzle, so then textile reinforcement goes in between, and then layer by layer, the reinforcement also lapped. And this is one method. There's another method. We can print the formwork using the concrete, geopolymer concrete, or ultra high performance concrete, and we so the external part of the formwork is printed, so we can achieve any shape, texture you like, and then we put the reinforcement inside, and we put the pour the concrete inside, and the formwork then become part of the structure. So this is another technology that we're working on, and that's is less complicated.
So as a researcher, what I want to say is don't get limited to the lab. Of course, what we have to really try now is taking the things that we do in the lab to the industry. Search for industry collaborations, do more industry preferable research, and always target what is the application and try to bring this product to reality. If not, there is no purpose of what we are doing, because we do in the lab but nothing's happening. So our aim as researchers is to do the research and take it to the field and go for a real application to make the actual impact.